Okay, all right. It's not a big deal. Many more complicated situations in my life.
Ja, soweit. Wir haben ja gestrichen und ein bisschen umgebaut. Von daher etwas arbeitsam.
Guter Urlaub.
Ja. Ja, ich habe ja hier mein Büro, siehst du vielleicht im Hintergrund, hat sich jetzt etwas geändert, weil wir schon auf Kinderzimmer umgebaut haben.
Ja, schön. Wann bist du wieder im Büro?
Hello.
Morgen.
Morgen, okay.
Hallo.
Morgen, Dimitri.
Brauchst du denn was, oder?
Eine Unterschrift brauche ich von dir.
Achso, alles klar, kein Thema.
Aber sonst. So, Dimitri, dann.
Yeah. So we check the Zoom. Like, can you hear me? Good.
Yeah.
I can try to show my presentation if it's working all right. So.
Yes, but I have to co-host. I think now you can try it.
Can you see the screen, right?
Yeah, now I can see your complete home screen. Yeah,
like this.
Yeah, nice.
Can I ask you a question? Do you also see? Do you see this to the right, me and yourself?
Yeah.
Because I was afraid that I can somehow, like, there will be much more people, and it can like cover the slides, you know, a little bit.
Yeah, but I can close it. So everybody is able to close that. I can close the complete screens. Then I can only show you.
Okay.
For me, and then I can see everybody who's participating. So I think that everybody can handle it.
Okay, no problem then.
That should be no problem.
Okay, so it's working. Nice.
Yeah, it's working.
Cool.
Yeah, very good. How are you? Are you good?
Yeah, I'm alright. I'm ready. No problem. But is the start of my presentation 8:15, right? Or it's delayed?
No, it is 8:15. But yeah, it's very early, and I don't really know how many people will participate. Part in your presentation. So
it's not a problem. The most important people should be me and professor and examiners. That's it.
Yeah, that's right. And yeah, we have 5 minutes left, and I think Sebastian and also Dennis are the examiners.
Yeah, exactly.
Yeah. Okay, and your presentation is about 20 minutes?
Yes.
Yeah, okay, good. Yeah, 20 minutes presentation and up to 20 minutes questions. And after that, you will go out of the meeting. And I think you can use the same link.
I know. I just
have sent you to come back. And if you should come back, I think I will send you an email to come back to the room. So please look at your email account. I will use the RWTH email.
Yeah.
And yeah.
So. The same email where you sent me before, or?
Yes, the same.
Okay, good. No problem.
Or we can there's a possibility, let me look, to Freigabe. Cool. Mhm. Shit. Mhm. I'm looking because there should be an option that I can put you to the waiting room, and so you have not to completely leave the meeting.
Okay.
So but I don't know where to do it. Video stumm schalten, Safety. Teilnehmer entfernen. Löschen. Okay.
Guten Morgen zusammen.
Hallo.
Morgen.
So, guten Morgen.
Guten Morgen.
Morgen.
Wie viele sind wir denn?
5.
Es ist früh.
Ich sehe Nilüfer Farahani,
Ja, das
doch.
ist unser Gast.
unser Gast, alles klar.
Barbara? What about Barbara?
She should be there. Maybe we have approximately 2 minutes before start.
Okay. Good.
Volkan, bist du unser Moderator today, heute, oder ist Dennis das?
Ich bin der Moderator.
Okay.
Sebastian,
Ja.
es müsste eine Option geben, dass man Leute in den Warteraum verschieben kann und nicht ganz rausschmeißt für später bei der Notenvergabe. Weißt du, wie das
Ja.
geht? Du hast wahrscheinlich schon öfters mal mit Zoom gearbeitet.
Ich habe das mehrfach erlebt bei Promotionsprüfungen. Und das war in Zoom. Es gibt die sogenannte Breakout-Session. Bin ich der Host im Moment? Nee, ne?
Nee, aber ich kann dich zum Host machen. So, jetzt bist du Co-Host.
Ja, okay. Ich sehe mal, Moderator bin ich, mehr.
Okay, hier Breakout-Session erstellen. Ordnen Sie 6 Teilnehmer zu.
Wo hast du das gesehen?
Ganz unten im Reiter steht irgendwann Breakout-Session. Neben Reaktion und Aufzeichnen.
Okay, das habe ich noch nicht. Dann muss man vielleicht von Anfang an Host sein. Bei mir ist neben Reaktionen und Aufzeichnen Bildschirm freigeben und das war's. Aber dann kannst du das ja machen.
Ja, leider kann man hier, ich sehe hier keine genauen Einstellungen, wen man rausschicken kann und wen nicht. Also,
Die musst du antippen in der Teilnehmerliste.
Guten Morgen.
Guten Morgen
Morgen.
zusammen. Also alle wichtigsten Personen für den Anfang sind da. So, heute haben wir eine Präsentation, Masterpräsentation von Dmitri Nazaroy. Das Thema ist verbunden mit Ermüdung. Und ab jetzt, so from now, I will give the word to Dmitri. Dmitri, please
Okay.
on stage.
Hello everyone. So the official time of my presentation, it's 8:15, right? So basically, I don't know if it's okay. I can introduce myself first of all, and then I can start my presentation.
Excellent.
Please do it.
Okay. So my name is Dmitry Nazaroy, and I'm originally from Russia. My supervisor is Denis Novakshanov. So I'm 30 years old. I started studying in RVTA from 2017, metallurgy engineering. In IHK, I just started my HIVI first of all, then I did my mini thesis. Now I'm doing my master thesis. My background is laser technologies in machine building, and today's presentation is about additive manufacturing. When everyone is ready to listen to me, I can start my presentation. Can I?
Yes.
Amazing.
Please.
So, hello everyone once again. Today I will present my master thesis work called Fatigue Properties Investigation of Additive Manufactured Materials, and namely I investigated the anisotropy of fatigue crack propagation in additive manufactured specimens produced with different building orientation. Nowadays, the additive manufacturing experiencing high intensive development in different application fields such as automobile industry, aircraft industry, space industry, and etc. And in all of these industries, the materials produced by additive manufacturing are under the high cycling load, like for example engines, generators, or etc. So the materials, the components are exposed to fatigue, and in order to apply these materials more broadly in these fields, it is necessary to know the fatigue properties, to investigate their fatigue properties. But unfortunately, except titanium, aluminum, steels, the fatigue properties of additive manufactured materials are not well investigated. My goal was to fill this gap somehow. So I will start in giving insight a little bit about the additive manufacturing. So the additive manufacturing, it is procedure of creating the components from 3D computer models by adding the layer by layer. Two most famous techniques of additive manufacturing, it's direct energy deposition, where the material is supplied directly to the necessary spot with the energy, and also the second technique, powder bed fusion, with its most famous SLM, selective laser melting technology, where the metallic powder is supplied to the building plates and the laser selectively melts the material, creating the layer. This layer goes down, and new amount of powder is applied, and the procedure repeats again and again. This feature of production technology has its own influence on the microstructure, on the defects distribution, and etc. So you can see how independence of the building orientation, of course, and you can see how the porosity level is differentiated with regards to the building direction in vertical specimen and in horizontal specimen. It should be also noted that the microstructure of additive manufactured steels are elongated grains, columnar elongated grains, because the grains grow in the direction of heat transfer. And with regards to the applied notches, the crack could propagate along the columnar grains or transversive, and taking the shorter or longer routes, and it has an influence on the rate of crack propagation. I also will give some information about the fatigue propagation theory. So the crack propagation is comprised of incubation period, which is in my case was the time from the load application until the crack reaching the length of 1 millimeter. And the incubation period is also comprised of crack initiation. Normally the crack initiates from the surface in inclusions or from the cracks, but also the slip bands could serve as an initiation point. That follows by the long crack propagation, and the typical curve of crack propagation is presented on a figure 6, and it's comprised of 3 regions: the threshold region number 1, region number 2 it is the Paris law region, and the region number 3 unstable region. In this work, as it's normal for lab investigations, I tackled the problem, and the problem is the lack of the material. So in this circumstance of lack of the material, I had to choose, analyze, and choose the most appropriate method of testing fatigue properties. The most popular is the tension compression test, and analyze it. And in order to produce the specimen, tension compression specimen with the smallest diameter, it is required around 15 cubic centimeters of the material, and it's much more, for example, in comparison to the proposed small specimens. Another problem, it is the undesired failure in the grip area. For example, when the tension compression specimen with the threaded edges is not properly aligned with the main axe, it can cause the appearance of additional bending moments, and finally the failure could appear in the thread area. It's undesirable because we lose the priceless material, so this method is unacceptable. Therefore, the bending method is in priority, and the most popular bending method is the 3-point bending method, but in this case only the material under the maximum force is under the this material is brought to the maximum load, and any shift to the right, any shift to the left will have a negative influence on the results of the experiment. Therefore, it was chosen to take the 4-point bending method because the broader amount of material is brought to the maximum force. It's more convenient. But it should be also noted that it was taken a decision to create an artificial notch because it's meaningful. Without this notch, it was uncertain when and where the crack will appear. But before creating the notch, it should be taken into the consideration the microstructure of the given plates. In this experiment, we received 6 plates. Plate number 2 and 6 were printed flat on the surface, and therefore the notch was produced in such a way that the crack propagated perpendicular to the building direction. For the plate 4 and 5, which were produced and printed perpendicular on the flat surface, and these plates and specimens called vertical specimens. Here the notch was produced in such a way that the crack propagated coaxially to the building direction. With regards to the plate number 1 and 3, the crack was tilted to 45 degrees to the building direction. So the geometry, the specimen geometry was chosen like this: 530 centimeter cubic, and in order to produce the notch itself, but because the notch was a critical factor, since the notch geometry influenced the incubation period, it was necessary to create this equal conditions to all of the specimens. And in order to do that, the notch cutting device was assembled based on the diamond cutting wheel. The equipment to investigate the fatigue properties was chosen as the horizontal small pulsar with a maximum force of 3 kilonewton. On the picture to the left, zoom picture to the left, we see the optic system which made the high resolution photos of the crack propagation. Number 4, it is the specimen itself. Also, we can see the indirect lighting to better investigate, to better see the crack propagation. Number 3, it is the counter, which was used in order to count the amount of cycles. And also, it's important to say about the number 2, it is the shaft, which controlled the middle force by the handle, It was done manually during the experiment, so it has a certain influence on the results of the experiment. When the equipment was chosen, the method was chosen. The method was supposed to be verified, and first it was tested on a high strength structural S690 steel, which fatigue properties are well investigated. For that, the forces listed to the left were applied at stress ratio 0.5. That triggered the crack to propagate in such a way demonstrated on the figure 13. So the crack propagated in a direction of the in the direction of core of the specimen. The length was recorded with regards to the amount of cycles, and it turned into the AN curve, which is presented on a figure 14. By taking the slope of this curve, dA over dN data was received, and the stress intensity factor range was calculated according to this formula. Finally, we received the crack propagation curve for steel S690. These results were compared with the results in the literature, and curves showed the similar trend. So the method was approved, verified, and ready to for testing the fatigue properties of additive materials, additive manufactured materials. So it should be said that every single direction was presented by at least 6 specimens, and only one typical specimen was chosen, which presented the whole batch. And here we can see AN curves from the specimens produced with different building orientation, and it's obviously seen that the shorter incubation time was for vertical specimens, the longer for horizontal specimens. By applying the data reduction technique, the crack propagation curves were constructed, and it's obviously seen the scatter in the crack propagation curves with a slower crack propagation for horizontal specimens and fastest crack propagation for vertical specimens. Tilted specimens were showed the close results to the vertical specimens, but even though the crack propagated in the intermediate fashion. In order to explain all of these differences, it was taken a decision to investigate the microstructure, do the porosity analysis, and fractography analysis. Here the vertical specimen is presented, and on the side view of the fracture surface, the morphology of the specimen is the elongated columnar grains. Here we can see that the grains are even elongated beyond the laser tracks. And since the crack propagated coaxially with the elongated columnar grains, the crack cleaved down the length of columnar grains like similar to chopping the wood with an axe. And therefore the longitudinal distribution of the fracture surface was formed. Since the crack propagated coaxially, like alongside to the columnar grains, as I said, it propagated through the shorter routes, and that caused that result in a faster crack propagation. With regards to the porosity level, these specimens experienced shorter time interval, lower temperature gradient, and therefore slower cooling rate. Therefore, the material was a little bit overheated, and that resulted in a bigger diameter of the porosity. Therefore, that triggered additional crack propagation mechanism as jump over cavities. So that facilitated the fast crack propagation. Now we come to horizontal specimens, and on the side view of the fracture surface we see the morphology of equiax grains. And since the crack propagated perpendicular to the columnar grains, the transverse distribution fracture surface was formed. And in this case, the crack propagated through the longer roots, deviating and being hindered by the columnar grains. So that caused the longer crack propagation. With regards to the microstructure, these specimens, they experience longer time interval, higher temperature gradient, and therefore high cooling rates. That resulted in a smaller diameter of the porosity, which was distributed perpendicular to the columnar grains. So all of this feature resulted in the slowest crack propagation. And with regards to the tilted specimens, on the side view of the fracture surface, we see the morphology, something between columnar grains and equiax grains. And with regards to the porosity, it showed the smallest amount of porosity in comparison to vertical and horizontal specimens. All of this feature resulted in the crack to propagate in the intermediate fashion. On this picture, I listed all of this microstructure and porosity distribution in order to better understand how the building orientation influence on all of these parameters. And now I would like to come to the conclusion and say that in this work, a new 4-point bending test method was introduced. It was tested, verified, approved, and used to investigate the fatigue properties of high manganese X30 Mn22 steel samples produced with different building orientation. The anisotropy was determined, the fastest crack propagation rate for the vertical specimens. The source of anisotropy was determined as microstructure and porosity level. So the highest fatigue crack growth rate was in the longitudinal direction of the columnar grains. But for better understanding the whole picture of fatigue properties of high manganese strip steel fatigue properties of the steel, it is meaningful to carry out the further investigations and probably to consider other factors such as residual stresses, roughness, and micro cracks, so to better understand the properties. So here I would like to finish my presentation and say thank you very much for your attention. So I finished.
Yeah, thank you very much. Volkan.
Yeah, thank you. Any questions to Mr. Nazar's presentation?
If not, I can start.
Yeah, I have a question, Dennis, but please go ahead.
Okay. Dmitry, you work with high manganese steel, and this steel is quite difficult to measure, so to prepare the samples from this steel. How this issue was solved in your work?
How did I cut the specimens, you mean?
What kind of technology you use to prepare the samples?
I just so in order to cut the specimens, to create this geometry, I use this typical cutting device. It is listed, the name of this device is listed in my written work, but I don't remember. So it was about the cutting wheel. So the geometry was produced like this, and about the notch geometry I already explained. This also was assembled the specific equipment.
Okay, so it means we used diamond material to cut this.
Yeah, exactly.
Okay, thank you.
Okay, Mr. Nazaroy, so you pointed out in your presentation, on the one hand, some, let's say, microstructural influences on the fatigue crack growth behavior. In your outlook, you said, okay, but further investigations are required, and you listed some points that you could not properly care for, which are the residual stresses, but you also spoke about micro defects that might be present in the material due to the manufacturing process. My question is, since the microstructure itself is mainly a result of the, on the one hand, chemical composition, and on the other hand, the parameters of the printing of the sample, what would you do to improve the quality of the microstructure in terms of fatigue crack growth resistance?
So in order to improve,
how would you manipulate exactly? How would you manipulate the additive manufacturing parameters in order to achieve better results? Do you already have any idea what could be done?
Yes, actually, if we talk about the adjusting the additive parameters of the setup, it's one option. So basically, it's possible to adjust the input energy, because input energy is the most important factor, since it influences the overheating and etc. So the porosity appearance, for example, also that influences the heating rate. So also one of the parameter, it is the speed of printing, definitely. So it has an influence on the temperature. Besides that, so additionally, you can, for example, to get rid of residual stresses, you can you can do the additional heating of the printing plate, so they will reduce the residual stresses as well. Also you can do the post treatment, but yeah, so mainly parameters, it's the speed and the energy input of the setup.
Okay. One remark, what's about powder?
What about powder? Yeah, okay, the powder, you can also try to choose what is the most appropriate diameter of the powder, because, like, of course it has an influence, because powder could be not properly melted if it's too big, yeah. So it also has a influence porosity level, so these cavities, yeah. So you should also try it, but it's pretty complicated to have many different types of powder. It's, as I said, it's pretty expensive stuff. So.
Okay, Mr. Nazaroy, another question. So you were interested in the fatigue properties, and you already went with samples containing a notch, and you measured the fatigue properties by let's say, crack extension tests in order to achieve a dA, dN, delta K curve. I mean, the more basic test with respect to fatigue properties is simply a Wöhler test. Why didn't you go for this first?
Okay, Wöhler test, it is mostly to investigate the fatigue strength. So it's the time of the crack to appear. I would say that in my test it was somehow so the incubation time, actually, it is somehow the this Wöhler experiment. So I investigate the incubation time itself as well. But my point was to investigate the crack propagation. It's like dA over dN versus delta K curve. It's a bit different.
Okay. You know, one thing was really kind of surprising me in your thesis, because typically when people investigate steels in terms of fatigue properties, they say, okay, the microstructural influence is mainly in the early phase of fatigue damage. So in other words, with measures like grain refinement and so on that are typically used to control the strength properties of a material. You mainly affect the incubation time and the short crack growth, whereas most experts claim that the stage 3, the long crack growth, and also the fracture behavior is much less influenced by microstructural parameters, simply because in the early phases, the entire process is based on the dislocation slip, whereas long crack growth is mainly controlled by the applied delta K, and the entire material can be treated like a continuous homogeneous microstructure with more or less homogeneous properties. So the results you present here are somewhat surprising because they are, let's say, at least to a certain extent, not confirming the existing knowledge for steels, which were, and that makes the difference, of course, not produced by additive manufacturing.
Okay, I should comment that, or
if you like to comment, yes, that would be interesting to hear what you think.
That's what you said. It's absolutely right, because in literature it's also about that. But I would say that my method, the method which we introduced, so because of the small specimens, so we cannot see properly the all of these 3 stages. They're not the same. Like for example, when we take CT specimen and we see exactly like threshold region, Paris region, and the last like uncontrolled region. Here, because the specimen is too small, this is the disadvantage of this method. So we cannot like precisely like see you know this difference because of the crack propagated like 2 millimeter or something like this. This method is useful just to understand, to give the insight that the anisotropy exists, and it depends on the orientation. But for more precise, of course, it's not appropriate. It's just we need bigger specimens to give the to investigate how the microstructure influence, how the porosity level, etc. influence. So that's my comment.
Okay. One last question from my side, which is a very short one. I mean, you pointed out some anisotropy of the fatigue properties, and you, to my understanding, very correctly argue that this is the result of building the sample. Did you also check the anisotropy in the quasi-static strength properties by tensile tests?
Okay, no, actually I did not investigate the okay, I will answer this question because in our institute they are already investigated exactly this steel for tensile test, anisotropy, for the specimens built in different building orientations. So there was not like meaningful to do the same test to examine it. So I did something which was not before investigated.
Okay. So I'm done with my questions. I don't know about the others.
Okay, then we can close the question session and go to the next stage.
Okay, yeah, when there are no questions. Dimitri, wait a second. I will try something.
Okay.
2 sessions. Okay. So I will drag you into a breakout session. I hope it will.
If it works, Mr. Nazaroy, then please don't run away. This is simply another Zoom room. I guess you will be alone over there.
I know, I see already.
It's for our negotiations. We will call you back into this room.
Good.
To discuss the result with you.
Okay, good. See you later.
See you later.
Отличная комната. Было неплохо, короче. Чуть-чуть нервничал, но было, в принципе, неплохо. Чего нервничать? Интересно, сколько там людей было. Что-то я никого больше не видел, кроме только гостей и все.
Genau. Ja.
Ja.
Hallo.
Herr Nazaroy, können Sie mich hören?
Ja, genau.
Sie haben Ihr Mikrofon noch ausgeschaltet. Das heißt, wir können Sie nicht hören. Aber im Moment müssen Sie eigentlich auch nur zuhören.
Okay.
Ach so, eben.
English.
English. Sorry, Mr. Nazaroy. I was obviously confused. So everything back to English. Mr. Nazaroy, we cannot hear you because your microphone is muted. Anyway, we had to find two grades for you. One for the written thesis, which is, to my understanding, the more important one because it simply counts more, and also another grade for the presentation and for the questions and answers session, which gives you less contribution to the overall grade of this thesis. Mr. Nazaroy, we were impressed by both the written thesis and the presentation. Let me start with the presentation. You did a very good presentation, and in particular during the questions and answers session, you convinced us that you have gained a kind of expertise in the topic of fatigue testing, and also additive manufacturing. So we were impressed. There were some critical points. I have to mention this. There were some critical points about the structure of your presentation. So we were a little bit struggling, and therefore our discussion also took some moments longer than typical. But at the end, your good behavior during the questions and answers session made it possible for us to give you a 1.0 for the presentation. This is the best grade you can have. So we were really impressed by the way you did this. Then we also discussed your thesis. Also there we found plenty of really good things inside. At the end, the question is also how much of this amount of good results is the particular contribution of the candidate, and how much is also the result of a hopefully good supervision. And also this can then make a difference. At the end, we were convinced that nearly everything we have seen goes back to your own contribution, but there is a certain, let's say, contribution to the overall result coming from the supervision. And in our system, this leads to the fact that we give you a 1.3, which is almost the best grade you can have. And we were all sure that this is a very fair grade for your work. So congratulations for this excellent result of your master thesis. Thank you very much for doing your thesis with us. We all have learned something from your thesis, and maybe we can also use these results for our future activities. So congratulations, first of all, and thank you very much.
Yeah. Congratulations.
Thanks.
Good. You're all muted. I think.
Congratulations.
Yeah. Mr. Nazaroy, do you have questions?
I'm muted.
You have to unmute.
Okay, I can do it myself.
Now I muted you again. Sorry. No, not everybody at the same time. So I'm gonna. No, I can't. In fact, I didn't do.
Please switch on by yourself.
Yeah,
Try
exactly. Yeah.
Yes.
Yeah.
Okay, now you can hear me. Okay, cool.
Yeah.
So I've heard everything what you said. So the estimation, yes. Actually, I wrote. Dennis already asked me to write my self-estimation. I agree with the score. Like for written work, it's the same. What I said, it was not perfect, but it was, according to myself, was good. So yeah, I'm satisfied with everything what you said. So I did my best, I would say. So I'm happy.
Okay, that's obvious. Is it the end of your studies now, or do you have some exams?
Also, I have to do internship. That's the last thing.
Internship is the last thing. Okay, then congratulations for finishing the thesis. I cannot congratulate you for finishing all your studies because the internship is missing. But I think this is not really something critical. Internship is simply something you have to do. You already found your place?
Not yet.
Yeah.
But soon I'll find.
I hope so. It's a little bit complicated, I guess, due to the Corona situation. But I wish you all the best for this.
Thank you very much.
Mr. Nazaroy, I think we're at the end. So we can stop the session now. Go and celebrate yourself today. But come back tomorrow.
Good. Thank you very much for all of you, for listeners.
Okay. Then have a nice day.
Tschüss.
Okay. Tschüss.